All right, let's look a little more generally. The Taylor polynomial of f of x at a. So now we're centering at any value that we like. How is that going to change what we do with the Taylor polynomial? So we're still going to call it, it's the nth degree, so it's still p sub n of x. Here's what changes. Instead of x raised to the k, it's x minus a to the k. So that minus a, it performs a shift, and now we end up centering at a itself, right? We're going to define the coefficient in front slightly differently. We still take derivatives. It's still over k factorial, but what we plug in isn't 0 anymore. It's that value a where we're centering. Okay. If you'd like that in the expanded form, it's usually easier to wrap your head around that way. So we'll begin with the original function at a over 0 factorial x minus a raised to the 0. Then we'll add the first derivative at a, 1 factorial x minus a to the first. And we'll keep going in that pattern, right? The second derivative at a over 2 factorial x minus a squared, however many terms we need until we have the nth degree, whatever that is. All right, let's jump into an example. Find the Taylor polynomial of f of x at a. So we're going to look at f of x equals 5e to the 2x. We're going to find p3 of x, the degree 3, and we're going to center at a equals 1. Okay, let's see how it goes. So we notice, hey, it's degree 3, so I need the original function plus 3 derivatives, and then I'm going to plug this into each one of them. Those are going to be my numerators. Well, we really like e when it comes to Taylor polynomials because their derivatives are so nice. So there's our original, and we plug in 1, 5e squared. You definitely want to leave it as 5e squared. You don't want to round these, so we'll take it like that. Okay. Our derivative, well, there'd be a chain rule, right? We would multiply down by 2, and we'll plug 1 into that, 10e squared. Our second derivative, multiplying down by 2 again, 20e to the 2x, plugging in 1, 20e squared. And we need the third derivative. We're going to stop here for degree 3, multiplying down by 2 again, 40e to the 2x, plugging in 1, 40e squared. Okay, so those derivatives work out pretty quick. Really nice. And plugging in is also very simple. All right, well, just like before, these are going to be the 4 numerators to our terms. So I'll just show you this. This is the end of my page. Our third degree Taylor polynomial, 5e squared over 0 factorial. And now this changes well, x minus 1, because we're doing that shift to center it at 1, x minus 1 to the 0. 10e squared over 1 factorial, x minus 1 to the first. 20 squared over 2 factorial, x minus 1 squared. And finally, 40e squared over 3 factorial, x minus 1 to the third. Okay. Last thing we got to do is just simplify whatever we can. And really all we're simplifying each time are these fractions, right? With those factorials. And so I couldn't fit, for some reason I didn't want to fit this all on one line. Like I thought it might not fit on the screen. So here it is, that first one, 5e squared. The next one, well, it's over 1 factorial into the first, so 10e squared times x minus 1. This one, it was 20 over 2 factorial. Well, that simplifies to 10. And okay. And the last one was 40 over 3 factorial. Well, that simplifies to 20 over 3 e squared x minus 1 to the third. And this works really well for an answer. Some people, though, notice, I can tell all of these terms have an e squared, and they actually all have a 5 as a factor as well. Could we factor out, say, 5e squared? certainly can. You might even do that from the beginning just to make it easier to write out. And then you'd have what, 1 plus 2 times x minus 1 plus 2 x minus 1 squared plus 4/3 x minus 1 to the third. That's great. Love it. Either way. Hopefully Math Excel would take that factored version. I can't guarantee that. Okay, we have one more problem to do. It's an application. So let me show you this whole thing here. Fit it on the screen a little bit better. Okay, let's go. Say the price demand of a certain commodity is this: P equals 1/5 times the square root of 1600 minus x squared. Think, okay, no big deal. If I know the demand of my commodity X, this is how many I'm going to sell in a given month or week or whatever it is, then I know how to set the price. So I sell that many, right? What's the problem? Well, look at what they're asking us to do. Use, the second degree polynomial. All right, these are our instructions, but that's not really why. Use the second degree Taylor polynomial. We're going to center at 0 to approximate the average price over 0 to 30 for x. Okay, focus on that. Find the average price from 0 to 30. What would that mean? If you want to know the average of your, however you're defining your function, here it's price. If you want to know the average over some interval of x, you would have to do this. You'd have to integrate over that integral, 0 to 30. Okay. And then you multiply it by 1 over, and you take the difference there. So 30 minus 0 goes right there. So in our case, it's 1 over 30 integral 0 to 30 for our function dx. You're like, okay, so what? We've taken tons of integrals in this course. And at the beginning of the course, right, we learned some integration techniques. Yes, but we have no technique for that function right there. 1/5 square root 1600 minus x squared. And that's my little note here. What is that antiderivative? I have no idea. Okay, so this is like another side of the application of Taylor polynomials. Check this out. What we're going to do, we're going to approximate this with a polynomial. Okay, we're going to find the second degree polynomial to approximate that. Then we'll easily just put that polynomial in here, and we can easily do that antiderivative of the polynomial. This is a massive, massive, massive the usefulness of calculus when it comes to where you see it in the real world. Who knows what you might have to integrate at any given time to get what you want. You're like, but I don't know how to take that antiderivative. Okay, but I can put it into a computer, and the computer can figure out the antiderivative. And the computer, the reason it can do it is because it doesn't think of it the way we do. It can think of it as this really highly accurate polynomial. All right, anyway, I'm laid out my strategy in words as well. We're going to find the second degree polynomial for that function right there. Then we're going to put our second degree polynomial, integrate that, and we'll do the average, so the 1 over 30 comes in also. Okay, that's our game plan. Let's execute. So I know if I'm looking for the second degree Taylor polynomial, I'm going to have the original function, and I'm going to need 2 derivatives. So I've rewritten this as to the 1/2 power. Okay. Here's my first derivative, and I went ahead and simplified. So, well, maybe I'll just show you this for now. So we're doing a chain rule. Okay, this is really no big deal. 1/10, 1600 minus x squared to the negative 1/2 times our inside function, negative 2x. We can simplify a little bit, make it negative 1/5 x, 1600 minus x squared to the negative 1/2. All right, we also need a second derivative. Well, for a second derivative, I'm going to apply a product rule. So I've got my first part, my second part for my product rule. And I don't think it's all on the screen yet. Okay, there it is. So derivative there, negative 1/5, and copy, plus I'll copy that part. And then for the last part of my product rule, I need the derivative of that. So negative half 1600 minus x squared to the negative 3/2, and then the chain rule times negative 2x. Okay, well, I don't want to bore you with just taking derivatives. You know, it's going to change from problem to problem. I'm going to simplify that second derivative. So there's my first part, and then got some negatives to cancel there. The 2 and the half cancel. 1/5 x squared, 1600 minus x squared to the negative 3/2. Okay, so, well, you could see anything when you tackle problems like this. I'm glad we only needed 2 derivatives here and not 3 or 4. Okay, so because these derivatives were a little bit more lengthy, I didn't put the evaluations next to them. We're centering at 0, the problem said. So we're going to plug 0 into each one of these functions, and I did that right down here. I don't know if it'll all fit on the screen. Hopefully you're writing this down. I'm just going to show you this right there. So the original function at 0 turns out to be 8. The first derivative at 0 turns out to be 0 because we had an x multiplying. The second derivative at 0 turned out to be negative 0.0005, and I was happy with the decimal version in that one. Okay, so those are going to be our 3 coefficients in our degree 2 polynomial, right? 8, 0, negative 0.0005. And of course we have our 0 factorial, 1 factorial, 2 factorial. We're centering at 0, so we just have x, and it's raised to the 0, to the first, to the second. Okay, now if we simplify with those factorials, well, of course that middle one's just gone. So here it is, 8 minus 0.00025 x squared. Okay, so this second degree polynomial turns out is a very good approximation of that original function 1/5 square root 1600 minus x squared if you're nearby 0. And that's going to be fine for us. So we're going to take this second degree polynomial and we're going to put it into our integral. So we're just going to say, forget that original function. I like this. It's accurate enough, so I'll integrate from 0 to 30. I'll multiply by 1/30 to get the average from 0 to 30. And perfect. I mean, this is awesome. I don't have to do any crazy integral technique. Right? 8x. This one over 3 to the third power from 0 to 30. So plugging 30 in, plugging in 30, I got into just what's in the parentheses there, 237.75. Of course, plugging in 0 is 0. Final answer, 7.925. That is the average price for x between 0 and 30. Okay. Well, I hope you enjoyed this section as much as I did. Good luck in the homework. See you in the live meeting.